Welcome to Shanti-Peace for mathematics. So in the previous video we have talked about fxy at AB is not equal to fyx at AB in general, and we have solved certain examples in which this condition is not satisfying. At the end of the video I raised the question that under which situation these mixed partials are equal. The solution for that is developed by Schwartz. His name, this is a Schwarz theorem is there. So let us state what is this theorem says. So let f will be the mapping from D to R, where D is a subset of R square, be a function, and x0 y0 it is in D if the first condition fy exists at x0 y0 and second one xy is continuous at x0 y0, then prove that fyx is also exist at x0 y0 and fxy at x0 y0 is same as fyx at x0 y0. So this is the Schwarz theorem. It tells you that fy, that is the first order partial derivative at y, is exist at that point. Also the second order partial derivative, that is the mixed partials, is continuous at that point. Then we can say that the another mixed partial, that is fyx, is also exist, and also we can say that the mixed partial, that is fxy at that point, is same as fyx at that point. So if these two conditions are satisfied, then we can say that the mixed partials are equal. Let us try to discuss the proof of this theorem. I will highly suggest that while doing the proof you will sit with the note and pen, because the proof is lengthy. Let's consider n be the neighborhood of x0 y0 such that this neighborhood, entire neighborhood, should be lies inside the domain D. Now I am defining one function phi of hk as f of x0 plus h y0 plus k minus f of x0 plus h comma y0 minus f of x0 y0 plus k plus f of x0 y0. And I am calling this is as equation 1. Also define g of x is equal to f of x comma y0 plus k minus f of x y0. I am calling this is as equation 2. Now in equation 2 you just put x is equal to x0. So putting x is equal to x0 in 2, we have g of x0 will be f of x0 y0 plus k minus f of x0 y0, and if you put x is equal to x0 plus h into, we get g of x0 plus h is equal to f of x0 plus h y0 plus k minus f of x0 plus h y0. If I call it this equation 3 and this one is as a 4, now with the help of this equation 3 and 4 we can write down equation 1. So just see that what is equation 1. So I may write using 3 and 4, we write phi of hk, that is in equation 1. So you just see that the first, what is f of x0 plus h y0 plus k minus f of x0 plus h y0, in equation 1 you can have, that is this quantity. So this is actually g of x0 plus h, and the second quantity, that is this, will be g of x0. We'll have this quantity is g of x0 plus h minus g of x0. I'm calling this equation as 5. Now given that fxy exists at point x0 y0, so given that this fxy it exists, that means fx at y is there. So first of all fx is exists, then and only then we can calculate fxy. So that's why we can say that therefore fx is exist at x0, y0. Since fx is exist and fy is exist, therefore I can say that f is differentiable with respect to x in the neighborhood n. See, here I am talking about f as one function. F is a function of two variables, x and y. Since fx is exist, then we can say that a function is differentiable with respect to x, keeping your y coordinate constant, and that gives you from equation 2 that f involves here and here. So if f is differentiable with respect to x, we can say that g is also differentiable with respect to x in the neighborhood of x0, y0. That is this. So what we can say is g is differentiable with respect to x in the neighborhood. Now what is the, now g is a function of one variable, so it is has a neighborhood, it is n. So it is actually x0 to x0 plus h. In this neighborhood it is different. G is continuous and differentiable in this neighborhood. So therefore we can apply the Lagrange mean value theorem is there. So let us recall what is LMVT. The LMVT says that if f is continuous on closed interval x0 to x0 plus h, f is differentiable on open interval x0 to x0 plus h, then there exists some theta in closed interval 0 1 such that f dash of x0 plus theta h is equal to f of x0 plus h minus f of x0 upon h. Now due to this, since this g is differentiable, we can say that there exists theta belongs to 0 1 such that g of x0 plus h minus g of x0 upon h is equal to g dash of x0 plus theta h. Now what is this numerator? That is g of x0 plus h minus g of x0 due to equation 5. Equation 5 says that it is phi of hk. So that's why we can have, therefore this is phi of hk upon h is equal to g dash of x0 plus theta h. So hence we have phi of hk is h into g dash of x0 plus theta h. We call this is as equation number 6. Now what is g dash of x? Let us calculate this side. From equation 2 we have, what is equation 2? Let us see that. The equation 2 is this, that is g of x is equal to f of x y0 plus k f of x y0. G of x is equal to f of x y0 plus k minus f of x y0. So this will gives you g dash of x. If I differentiate this, this will, and this is the function of two things, so that's why it is fx at x comma y0 plus k minus fx at x y0. Now by replacing, if I want to calculate this quantity, then I am replacing x by x0 plus theta h. What we can have here, it is g dash of x0 plus theta h equal to fx at x0 plus theta h comma y0 plus k minus fx at x0 plus theta h comma y0. Now if you substitute this value into the equation 6, so if you substitute here that value, therefore we have phi of hk will be h into fx at x0 plus theta h y0 plus k minus fx at x0 plus theta h comma y0. Also given that fxy is continuous at x0 y0. I will call this as equations number 7. What is given is, another thing is fxy is continuous. So therefore what we can say is fxy is exist in the neighborhood of x0 y0. Therefore fx is differentiable with respect to y in some neighborhood y0 comma y0 plus. So here this is nothing but the fx and its derivative with respect to y. So I can say that this fx is partially differentiate. We can say that fx is differentiable with respect to y. Again, we are applying the LMVT for fx. By LMVT, there exists theta 1 belongs to open interval 0 1 such that fx at x0 plus theta h comma y0 plus k minus fx at x0 plus theta h comma y0 upon k is equal to fxy, because it is a derivative. The derivative is with respect to y. So that's why it is fxy x0 plus theta h comma y0 plus theta 1k. See, just notice that here this quantity is fixed, x0 plus theta h. So it is f of b, that is y0 plus k minus a, f of a, and then we'll have this quantity. Now what is this numerator? You just observe what is the numerator from equation number 7. The equation number 7 tells you that, so this quantity is phi of hk upon h. So that's why we can have this quantity is phi of hk upon h. So that's why it is phi of hk upon hk is equal to fxy x0 plus theta h y0 plus theta 1k. Hence we can have phi of hk, we can write as hk into fxy at x0 plus theta h y0 plus theta 1k. And if I apply the limit both sides with hk tends to 0, so therefore we'll have limit of hk tends to 0 phi of hk upon hk. On this side we'll have limit of hk tends to 0 fxy at x0 plus theta h y0 plus theta 1k. But what is this? Since fxy is continuous, so this side will gives you fxy at x0 y0. Now let us concentrate what will be this side. Finally what we have is fxy at x0 y0 will have limit hk tends to 0 0 phi of hk upon h into k. Now from equation number 1 that we have, what is the definition of phi of hk we have? So just see in your notebook which you have written, the phi of hk is actually we have defined as x0 plus h y0 plus k minus f of x0 plus h y0 minus f of x0 y0 plus k plus f of x0 y0 whole divided by hk. Now this quantity I may rewrite as limit hk tends to 0 0 1 upon h I can write down outside. I may write down this two quantity together divided by k, so that is f of x0 plus h y0 plus k minus f of x0 plus h y0 upon k, then it is minus f of x0 comma y0 plus k minus f of x0 y0 upon k. So finally what we have, it is limit h tends to 0 1 upon h I may write down outside, and this quantity if I take the limit k tends to 0 here, if I apply here and here, then this is keeping your x0 plus h fixed and you are changing in y only. So that's why it is f y at x0 plus h comma y0 minus f y x0 y0, because here is also you are fixing your x0 and you are changing in y, that is x0 y0 plus k to y0, and so this will be nothing but the fy fx at x0, y0. And on the other side we already have fxy at x0, y0. So that completes the proof of this result. I may suggest that you just watch this video again because the proof is lengthy and there are many steps where we are applying the Lagrange mean value theorem and the continuity of the function f of xy. You just see that and try to learn the proof. Here I want to write down one remark. It says that the converse of this result is not true. What is this result says? It says that fy is exist and fxy is continuous. This two quantity implies that fxy at some point AB is same as fyx at some point AB. This theorem is also can be written as fx is exist and fyx is continuous. Then also we have the same argument we can write. So that is the first remark I want to tell you. And the second remark that we can say that the converse of this result is not true. That we can see by an example. So let us have this example. F is defined from r square to r, defined as f of xy is equal to x square y square upon x square plus y square if xy is not equal to 0, 0, 0 if xy is 0. Prove that the first one fxy at 0, 0 is same as fy at x 0, 0, and the second one fxy is not continuous at 0, 0. So this theorem is actually gives you a converse of Schwartz theorem, because the Schwartz theorem says that fy is exist and fxy is continuous, then this condition is satisfying. But here what we are dropping this condition, that is fxy is not continuous, that we are saying, but still you will have this. It says that this condition is satisfying. We cannot say that fxy is continuous. To prove this one, let us try to discuss the proof of this. What is fx at 0, 0? Let us calculate first that. That is limit h tends to 0. F of 0 plus h comma 0 minus f of 0, 0 upon h is equal to limit h tends to 0. What is the function f at xy? The function f at xy, it is x square y square upon x square plus y square. So this is the function. This is h comma 0. So it is, if you substitute 0 here, it will gives me 0. So it is 0 minus 0 upon h. So finally you will have 0. Now let us calculate what is fxy at 0, 0. Fy at x 0, 0, that is k tends to 0. Fx at 0 comma 0 plus k minus fx at 0, 0 upon k. This quantity just we have calculated. I need to calculate what is fx at 0 comma k. Fx at 0 comma k, that we can calculate limit h tends to 0 f of 0 plus h comma k minus f at 0 comma k upon h. So this will give you limit h tends to 0. As per the definition, this is h square k square upon h square plus k square minus 0, because by definition this is upon h. This will gives you limit h tends to 0. This quantity is h square k square upon h into h square plus k square. One h is cancelled out here, and as h tends to 0, this is 0 upon 0 plus k square. So this will gives you 0. So finally what we have is fxy at 0, 0 is limit k tends to 0 fx at 0 comma k minus fx at 0, 0 upon k. This quantity we have calculated as 0. This is also 0. So finally you will have 0 here. Now fy at 0, 0, let us calculate that. Fy at 0, 0 is limit k tends to 0, f 0, 0 plus k minus f at 0, 0 upon k. So this will give you limit k tends to 0, 0 minus 0 upon k. So that will give me 0. And fy x is 0, 0. As per the definition, this is h tends to 0. Fy at 0 plus h comma 0 minus fy at 0, 0 upon k. Now let us calculate what is fy h comma 0. Fy h comma 0, as per the definition, this is limit k tends to 0, f h comma 0 plus k minus f of h comma 0 upon k. So by definition, this is limit k tends to 0, h square into k square upon h square plus k square minus 0 upon k, and 1 k is cancelled out, and as k tends to 0, this will give you. Finally, what we have is fyx at 0, 0 is limit h tends to 0, fy at h comma 0 minus fy at 0, 0 upon h. We have calculated this is 0, this is also 0, so finally we will have 0. So hence what we can say at fy at 0, 0 is same as fy x at 0. Finally what I need to prove is this fxy is not continuous. This is my objective at 0, 0. So before that I need to calculate what is fxy at any point. So first I have to calculate what is fx at y. So what is fxy? That we know it is x square y square upon x square plus y square if xy is non-zero. If xy is 0, this is 0. So first what is fx you will have, let us calculate that. So you have to apply the division rule here. X square plus y square as it is square, x square plus y square as it is. The derivative of x square plus x square into y square with respect to y, it is 2xy square minus x square y square as it is. The derivative of x square plus y square is 2x. So if you simplify this, this will give you 2x cube y square plus 2x y raised to 4 minus 2x cube y square upon x square plus y square whole square. So finally what we have is 2xy raised to 4 upon x square plus y square whole square. So what is fx at point xy will be this 2xy square upon x square plus y square if xy is non-zero, and 0 if xy is 0, 0. So now we need to calculate what is fxy. Fxy at any point, that is the partial derivative of this quantity with respect to x. So that we can have applying the division rule, that is x square plus y square power 4, we have x square plus y square whole square is a derivative with respect to y now. So the differentiation of this with respect to y, this power 4 you will have. So this will gives you 8xy cube minus 2xy raised to 4 as it is. Now derivative of x square plus y square whole square, that is 2 times x square plus y square into 2y. If you simplify this quantity now, you may verify that this will be 8x cube plus y cube upon x square plus y square whole power cube. By simplifying this, you may verify that this is the answer. So finally what we have is fxy at any point will have this 8x cube y cube upon x square plus y square whole cube if xy is non-zero, and 0 if xy is 0. Now we have to show that this function is not continuous. So it is enough to prove that this function's limit is not exist. So this I want to prove that this xy tends to 0, 0. fxy at point xy does not exist. So if I want to prove that this does not exist, then you have to take some path. So I am just taking a path as y equal to mx. So taking path y equal to mx. What will be the limit? Limit of xy tends to 0, 0. What is the function you will have? It is fxy at point xy. That will be the limit x tends to 0, fxy at x mx. And so this is limit x tends to 0. You can have the function is 8x cube y cube upon x square plus y square whole cube. This is the function. So that's why it is 8x cube m cube x cube upon x square plus m square x square whole cube. I just say in the numerator that is x power 6 is common out. Here in the denominator is also x square and its power 3. So that's why it is x power 6 is common out. And that cancel in the numerator and the denominator. So finally you will have limit x tends to 0. 8m cube upon 1 plus m square whole cube. So that is 8m cube upon 1 plus m square whole cube. And this is depends on m. So hence the limit is not unique. So therefore we can say that fxy is not continuous at 0, 0. And this completes the converse of Schwarz theorem is also. So in this video we have talked about the two things, the Schwarz theorem and its converse. The Schwarz theorem says that if fy is exist and fxy is continuous at some point, then at that point the mixed partials are same. The converse of this result is not true, that we have seen by example. From this I am stopping here. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in a comment box below. Till then, bye bye, sayonara.